The first very important thing to understand about the large language model space are what we call scaling laws. It turns out that the performance of these large language models in terms of the accuracy of the next word prediction task is a remarkably smooth, well-behaved, and predictable function of only two variables. You need to know n, the number of parameters in the network, and d, the amount of text that you're going to train on. Given only these two numbers, we can predict to a remarkable accuracy, with a remarkable confidence, what accuracy you're going to achieve on your next word prediction task. And what's remarkable about this is that these trends do not seem to show signs of sort of topping out. So if you train a bigger model on more text, we have a lot of confidence that the next word prediction task will improve. So algorithmic progress is not necessary. It's a very nice bonus, but we can sort of get more powerful models for free because we can just get a bigger computer, which we can say with some confidence we're going to get, and we can just train a bigger model for longer. And we are very confident we're going to get a better result. Now, of course, in practice, we don't actually care about the next word prediction accuracy, but empirically what we see is that this accuracy is correlated to a lot of evaluations that we actually do care about. So, for example, you can administer a lot of different tests to these large language models, and you see that if you train a bigger model for longer, for example, going from 3.5 to 4 in the GPT series, all of these tests improve in accuracy. And so as we train bigger models and more data, we just expect almost for free the performance to rise up. And so this is what's fundamentally driving the gold rush that we see today in computing, where everyone is just trying to get a bigger GPU cluster, get a lot more data, because there's a lot of confidence that you're doing that with, that you're going to obtain a better model. And algorithmic progress is kind of like a nice bonus, and a lot of these organizations invest a lot into it. But fundamentally, the scaling kind of offers one guaranteed path to success. So I would now like to talk through some capabilities of these language models and how they're evolving over time. And instead of speaking in abstract terms, I'd like to work with a concrete example that we can sort of step through. So I went to ChatGPT and I gave the following query. I said, collect information about Scale AI and its funding rounds, when they happened, the date, the amount, and the valuation, and organize this into a table. Now, ChatGPT understands, based on a lot of the data that we've collected, and we sort of taught it in the fine-tuning stage, that in these kinds of queries, it is not to answer directly as a language model by itself, but it is to use tools that help it perform the task. So in this case, a very reasonable tool to use would be, for example, the browser. So if you and I were faced with the same problem, you would probably go off and you would do a search, right? And that's exactly what ChatGPT does. So it has a way of emitting special words that we can sort of look at, and we can basically look at it trying to perform a search. And in this case, we can take that query and go to Bing search, look up the results. And just like you and I might browse through the results of a search, we can give that text back to the language model, and then based on that text, have it generate a response. And so it works very similar to how you and I would do research, sort of using browsing. And it organizes this into the following information. And it sort of responds in this way. So it collected the information. We have a table. We have series A, B, C, D, and E. We have the date, the amount raised, and the implied valuation in the series. And then it sort of provided the citation links where you can go and verify that this information is correct. On the bottom, it said that, actually, I apologize, I was not able to find the series A and B valuations. It only found the amounts raised. So you see how there's a not available in the table. So, okay, we can now continue this kind of interaction. So I said, okay, let's try to guess or impute the valuation for series A and B based on the ratios we see in series C, D, and E. So you see how in C, D, and E, there's a certain ratio of the amount raised to valuation. And how would you and I solve this problem? Well, if we were trying to impute not available, again, you don't just kind of do it in your head. You don't just try to work it out in your head. That would be very complicated because you and I are not very good at math. In the same way, ChatGPT, just in its head sort of, is not very good at math either. So actually, ChatGPT understands that it should use calculator for these kinds of tasks. So it, again, emits special words that indicate to the program that it would like to use the calculator and would like to calculate this value. And it actually, what it does is it basically calculates all the ratios, and then based on the ratios, it calculates that the series A and B valuation must be, whatever it is, 70 million and 283 million. So now what we'd like to do is, okay, we have the valuations for all the different rounds. So let's organize this into a 2D plot. I'm saying the x-axis is the date and the y-axis is the valuation of Scale AI. use logarithmic scale for y-axis, make it very nice, professional, and use grid lines. And ChatGPT can actually, again, use a tool. In this case, like it can write the code that uses the matplotlib library in Python to graph this data. So it goes off into a Python interpreter, it enters all the values, and it creates a plot. And here's the plot. So this is showing the date on the bottom, and it's done exactly what we sort of asked for in just pure English. You can just talk to it like a person. And so now we're looking at this and we'd like to do more tasks. So for example, let's now add a linear trend line to this plot, and we'd like to extrapolate the valuation to the end of 2025. Then create a vertical line at today, and based on the fit, tell me the valuations today and at the end of 2025. And ChatGPT goes off, writes all of the code, not shown, and sort of gives the analysis. So on the bottom, we have the date, we've extrapolated, and this is the valuation. So based on this fit, today's valuation is 150 billion, apparently, roughly. And at the end of 2025, Scale AI is expected to be $2 trillion company. So congratulations to the team. But this is the kind of analysis that ChatGPT is very capable of. And the crucial point that I want to demonstrate in all of this is the tool use aspect of these language models and in how they are evolving. It's not just about sort of working in your head and sampling words. It is now about using tools and existing computing infrastructure and tying everything together and intertwining it with words, if that makes sense. And so tool use is a major aspect in how these models are becoming a lot more capable, and they can fundamentally just like write a ton of code, do all the analysis, look up stuff from the internet and things like that. One more thing, based on the information above, generate an image to represent the company Scale AI. So based on everything that was above it in the sort of context window of the large language model, it sort of understands a lot about Scale AI. It might even remember about Scale AI and some of the knowledge that it has in the network. And it goes off and it uses another tool. In this case, this tool is DALL-E, which is also a sort of tool developed by OpenAI. And it takes natural language descriptions and it generates images. And so here, DALL-E was used as a tool to generate this image. So yeah, hopefully this demo kind of illustrates in concrete terms that there's a ton of tool use involved in problem solving. And this is very relevant and related to how a human might solve lots of problems. You and I don't just like try to work out stuff in your head. We use tons of tools. We find computers very useful. And the exact same is true for large language models. And this is increasingly a direction that is utilized by these models. Okay, so I've shown you here that ChatGPT can generate images. Now, multimodality is actually like a major axis along which large language models are getting better. So not only can we generate images, but we can also see images. So in this famous demo from Greg Brockman, one of the founders of OpenAI, he showed ChatGPT a picture of a little MyJoke website diagram that he just sketched out with a pencil. And ChatGPT can see this image, and based on it, it can write a functioning code for this website. So it wrote the HTML and the JavaScript. You can go to this MyJoke website and you can see a little joke and you can click to reveal a punchline, and this just works. So it's quite remarkable that this works. And fundamentally, you can basically start plugging images into the language models alongside with text. And ChatGPT is able to access that information and utilize it. And a lot more language models are also going to gain these capabilities over time. Now, I mentioned that the major axis here is multimodality. So it's not just about images, seeing them and generating them, but also, for example, about audio. So ChatGPT can now both kind of like hear and speak. This allows speech-to-speech communication. And if you go to your iOS app, you can actually enter this kind of a mode where you can talk to ChatGPT just like in the movie Her, where this is kind of just like a conversational interface to AI, and you don't have to type anything, and it just kind of like speaks back to you. And it's quite magical and like a really weird feeling. So I encourage you to try it out. Okay, so now I would like to switch gears to talking about some of the future directions of development in large language models that the field broadly is interested in. So this is kind of, if you go to academics and you look at the kinds of papers that are being published and what people are interested in broadly, I'm not here to make any product announcements for OpenAI or anything like that. This is just some of the things that people are thinking about. The first thing is this idea of system 1 versus system 2 type of thinking that was popularized by this book, Thinking Fast and Slow. So what is the distinction? The idea is that your brain can function in two kind of different modes. The system 1 thinking is your quick, instinctive, and automatic sort of part of the brain. So for example, if I ask you what is 2 plus 2, you're not actually doing that math. You're just telling me it's 4 because it's available, it's cached, it's instinctive. But when I tell you what is 17 times 24, well, you don't have that answer ready. And so you engage a different part of your brain, one that is more rational, slower, performs complex decision making, and feels a lot more conscious. You have to work out the problem in your head and give the answer. Another example is if some of you potentially play chess, when you're doing speed chess, you don't have time to think. So you're just doing instinctive moves based on what looks right. So this is mostly your system one doing a lot of the heavy lifting. But if you're in a competition setting, you have a lot more time to think through it, and you feel yourself sort of like laying out the tree of possibilities and working through it and maintaining it. And this is a very conscious, effortful process. And basically, this is what your system 2 is doing. Now, it turns out that large language models currently only have a system 1. They only have this instinctive part. They can't like think and reason through like a tree of possibilities or something like that. They just have words that enter in a sequence. And basically these language models have a neural network that gives you the next word. And so it's kind of like this cartoon on the right where you're just like laying tracks. And these language models basically, as they consume words, they just go chunk, 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 chunk. And that's how they sample words in a sequence. And every one of these chunks takes roughly the same amount of time. So this is basically large language models working in a system 1 setting. So a lot of people, I think, are inspired by what it could be to give large language models a system 2. Intuitively, what we want to do is we want to convert time into accuracy. So you should be able to come to ChatGPT and say, here's my question, and actually take 30 minutes. It's okay. I don't need the answer right away. You don't have to just go right into the words. You can take your time and think through it. And currently, this is not a capability that any of these language models have, but it's something that a lot of people are really inspired by and are working towards. So how can we actually create kind of like a tree of thoughts and think through a problem and reflect and rephrase and then come back with an answer that the model is like a lot more confident about. And so you imagine kind of like laying out time as an x-axis and the y-axis would be an accuracy of some kind of response. You want to have a monotonically increasing function when you plot that. And today that is not the case, but it's something that a lot of people are thinking about. And the second example I wanted to give is this idea of self-improvement. So I think a lot of people are broadly inspired by what happened with AlphaGo. So in AlphaGo, this was a Go playing program developed by DeepMind. And AlphaGo actually had 2 major stages. The first release of it did. In the first stage, you learn by imitating human expert players. So you take lots of games that were played by humans. You kind of like just filter to the games played by really good humans. And you learn by imitation. You're getting the neural network to just imitate really good players. And this works, and this gives you a pretty good Go playing program, but it can't surpass human. It's only as good as the best human that gives it the training data. So DeepMind figured out a way to actually surpass humans. And the way this was done is by self-improvement. Now, in the case of Go, this is a simple closed sandbox environment. You have a game, and you can play lots of games in the sandbox, and you can have a very simple reward function, which is just winning the game. So you can query this reward function that tells you if whatever you've done was good or bad. Did you win? Yes or no? This is something that is available, very cheap to evaluate, and automatic. And so because of that, you can play millions and millions of games and kind of perfect the system just based on the probability of winning. So there's no need to imitate. You can go beyond human. And that's in fact what the system ended up doing. So here on the right, we have the ELO rating, and AlphaGo took 40 days in this case to overcome some of the best human players by self-improvement. So I think a lot of people are kind of interested in what is the equivalent of this step number 2 for large language models, because today we're only doing step 1. We are imitating humans. There are, as I mentioned, there are human labelers writing out these answers, and we're imitating their responses. And we can have very good human labelers, but fundamentally, it would be hard to go above sort of human response accuracy if we only train on the humans. So that's the big question. What is the step 2 equivalent in the domain of open language modeling? And the main challenge here is that there's a lack of a reward criterion in the general case. So because we are in a space of language, everything is a lot more open, and there's all these different types of tasks. And fundamentally, there's no like simple reward function you can access that just tells you if whatever you did, whatever you sampled, was good or bad. There's no easy to evaluate fast criterion or reward function. But it is the case that in narrow domains, such a reward function could be achievable. And so I think it is possible that in narrow domains, it will be possible to self-improve language models. but it's kind of an open question, I think, in the field, and a lot of people are thinking through it, of how you could actually get some kind of a self-improvement in the general case. Okay, and there's one more axis of improvement that I wanted to briefly talk about, and that is the axis of customization. So as you can imagine, the economy has like nooks and crannies, and there's lots of different types of tasks, large diversity of them. And it's possible that we actually want to customize these large language models and have them become experts at specific tasks. And so as an example here, Sam Altman a few weeks ago announced the GPTs App Store, and this is one attempt by OpenAI to sort of create this layer of customization of these large language models. So you can go to ChatGPT and you can create your own kind of GPT. And today, this only includes customization along the lines of specific custom instructions, or also you can add knowledge by uploading files. And when you upload files, there's something called retrieval augmented generation, where ChatGPT can actually like reference chunks of that text in those files and use that when it creates responses. So it's kind of like an equivalent of browsing, but instead of browsing the internet, ChatGPT can browse the files that you upload, and it can use them as a reference information for creating its answers. So today, these are the kinds of two customization levers that are available. In the future, potentially, you might imagine fine-tuning these large language models, so providing your own kind of training data for them, or many other types of customizations. But fundamentally, this is about creating a lot of different types of language models that can be good for specific tasks, and they can become experts at them instead of having one single model that you go to for everything. So now let me try to tie everything together into a single diagram. This is my attempt. So in my mind, based on the information that I've shown you and just tying it all together, I don't think it's accurate to think of large language models as a chatbot or like some kind of a word generator. I think it's a lot more correct to think about it as the kernel process of an emerging operating system. And basically this process is coordinating a lot of resources, be they memory or computational tools, for problem solving. So let's think through, based on everything I've shown you, what an LLM might look like in a few years. It can read and generate text. It has a lot more knowledge than any single human about all the subjects. It can browse the internet or reference local files through retrieval augmented generation. It can use existing software infrastructure like calculator, Python, etc. It can see and generate images and videos. It can hear and speak and generate music. It can think for a long time using the system too. It can maybe self-improve in some narrow domains that have a reward function available. Maybe it can be customized and fine-tuned to many specific tasks. And maybe there's lots of LLM experts almost living in an app store that can sort of coordinate for problem solving. And so I see a lot of equivalence between this new LLM OS operating system and operating systems of today. And this is kind of like a diagram that almost looks like a computer of today. And so there's equivalence of this memory hierarchy. You have disk or internet that you can access through browsing. You have an equivalent of random access memory, or RAM, which in this case for an LLM would be the context window of the maximum number of words that you can have to predict the next word in a sequence. I didn't go into the full details here, but this context window is your finite precious resource of your working memory of your language model. And you can imagine the kernel process, this LLM, trying to page relevant information in and out of its context window to perform your task. And so a lot of other, I think, connections also exist. I think there's equivalence of multi-threading, multiprocessing, speculative execution. There's equivalence of, in the random access memory in the context window, there's equivalence of user space and kernel space, and a lot of other equivalents to today's operating systems that I didn't fully cover. But fundamentally, the other reason that I really like this analogy of LLMs kind of becoming a bit of an operating system ecosystem is that there are also some equivalents, I think, between the current operating systems and what's emerging today. So for example, in the desktop operating system space, we have a few proprietary operating systems like Windows and Mac OS, but we also have this open source ecosystem of a large diversity of operating systems based on Linux. In the same way here, we have some proprietary operating systems like GPT series, Cloud series, or BART series from Google, but we also have a rapidly emerging and maturing ecosystem in open source large language models, currently mostly based on the Llama series. And so I think the analogy also holds for this reason in terms of how the ecosystem is shaping up. And we can potentially borrow a lot of analogies from the previous computing stack to try to think about this new computing stack fundamentally based around large language models orchestrating tools for problem solving, and accessible via a natural language interface of language.